Okay, welcome to EGR445. In today's class, we are gonna continue our discussion on the helical gears. So one of the problem with helical gears is we get side thrust. So for an example, if you look at a helical gear, the helical gear is strong because the teeth are cut at an angle. So this is how the helical gear looks like. But rather than a spur gear, the teeth are cut at an angle. This angle is called as the helix angle. Because of that, you would observe the force is going to be in this direction. What that means is when you resolve this force, you are going to have a component of force in the axial direction. So you are going to get FA, which is force in axial direction. Now to compensate for the force in the axial direction, what we do is we actually have something called as herringbone or double helical gear. So in the double helical gear, you have two helical gears, but they are cut opposite to each other. So you have gear left side like this, right side like this. And the advantage of herringbone gear or double helical gear is the thrust. One gear, so I'll show you, will have axial thrust to going towards left, and the other gear would have axial thrust going towards right. And assuming the helix angle is the same, and it will be same, these two gear forces, they cancel each other. And herringbone gear or helical gear, they are used when the gear train needs to be extremely strong and the power requirement is quite high. So helical gear design process is exactly same as the spur gear. The only difference is, first we take the helical gear, and convert that into an equivalent spur gear. Bear with me for a second because Zoom is connecting. Yeah, Wi-Fi is connected. Okay, so force in the axial direction. So here you would observe that the first step is get the helical gear, and convert that into an equivalent spur gear. And then the design process remains the same. Continue with design. So in helical gear, alpha is the helix angle. And TE are the equivalent number of teeth on helical gear, or sorry, on spur gear, which is equal to T divided by cosine cube alpha. So for an example, if helical gear has number of teeth is equal to 16, then equivalent spur gear would have T divided by cosine cube alpha, and say alpha is 20 degrees. So it would be 16 divided by cosine cube 20. And what would happen is you would design the helical gear as if it's a spur gear with slightly more number of teeth. The other important dimensions for the helical gear are helix angle, that can go between 15 to 25 degrees in the plane of rotation. Addendum, which is 0.8 times module. Dedendum, which is equal to 1 times module. Minimum total depth, (1.8 times module). Minimum clearance, is equal to 0.2 times module. Thickness of tooth, 1.57 times module. And typically, just like spur gear, when you design a helical gear, P, which is power, and N, which is equal to speed, would be given. Sometimes the material properties would also be specified. If the material properties are not given, then we can use the data book and find out the appropriate material for that particular application. So now, just like spur gear, I want to give you the design recipe, and then we will work out a problem following the design recipe. The steps are identical. So design process for helical gears. Design process for helical gears. So first, power is equal to 2 pi nt divided by 60, and torque is given in Newton meter. Now, one thing that you want to find out is you want to find out WT. WT is equal to the service factor CS multiplied by P divided by pitch line velocity VP, which is pi times dN divided by 60. And D is nothing but the pitch circle diameter, PCD, which is pi times module. Sorry, module times number of teeth. Before you proceed to the next step, you want to make sure to do the weakness calculation. So what you do is you multiply sigma naught by sigma V, CV, which is the velocity factor for pinion, sigma naught by CV for the gear, and out of that find the weakest element. So you would multiply sigma naught by CV, sigma naught by CV for the pinion, for the gear, and then see which one is the weakest. This is CW, CW, and then you can do CWY prime, CWY prime for pinion and gear. So once you do that, you will understand out of these two, which one is weaker. And weaker element needs to be designed. So, but if the gear and pinion are made up with same material, then naturally pinion is going to be weaker. So the equation that we use is same as the equation that we used for the spur gear, and that is sigma naught CV multiplied by B multiplied by pi multiplied by M multiplied by Y. But this Y is Y prime, which is modified Lewis form factor. So what is the difference? Typically, Y value is found out based on T for the spur gears. So Y is found out using T for spur gears. For helical gears, we have to find out Y prime using T equivalent for helical gears. So step one is, once you decide the number of teeth, once you find the number of teeth, you have to find out the equivalent number of teeth. And then from equivalent number of teeth, you have to find out the appropriate Lewis's form factor. And that is an important step. Just don't use the number of teeth corresponding to spur gear and proceed. Basically, just find out the modified Y prime or modified Lewis's form factor. So this is the first step. And typically, the face width B will be given in terms of module. So this entire equation, typically from this entire equation, we will get value of module. And once we find the value of module, the basic dimensions are known. For CV value, you can use the CV value for the spur gear. This is the velocity factor. The equations are same as spur gear, and otherwise the procedure is same. Sigma naught is also same for spur gear because it's the material property. And step number 2 is finding dynamic load. So in dynamic load, WD is equal to WT plus, equation is slightly different, B times C. Please note here there is cosine cube alpha plus WT divided by 21V plus square root of B C cosine square alpha plus WT multiplied by cosine alpha. So don't forget, this alpha is the helix angle. And something to think about, for spur gears, helix angle is 0. So if you were to substitute alpha is equal to 0 in this equation, you are going to get the dynamic load equation for the spur gear. So this is something to note, side note. Alpha is equal to 0 for spur gears. Step 3. So we have to find out static load. Ws is equal to sigma E times B pi times M times Y prime. Now sigma E is the endurance limit. And please note the table that we use to find endurance limit is same as spur gear. So the tables are the same. B is the face width, M is the module, Y prime is the modified Lewis's form factor. And for design to be safe, this has to be greater than the dynamic load that we calculated in the earlier step. Step 4 is we have to find out the wear load, and wear load is given as WW. Equation is dP times B times Q times K divided by cosine square alpha. And here are some other equations that you can actually use. K is given as sigma ES, which is the surface endurance limit, times sine phi n 1 divided by EP plus 1 divided by EG divided by 1.4. And here is an important equation that I want you to understand. Here we have this normal, the pressure angle, which is sort of normal. So this is in normal direction. And the equation for that is tan phi n is equal to tan phi, which is the pressure angle, times cosine alpha, which is the helix angle. So this is helix angle. This is the pressure angle. But please note, what we need is phi n, which is pressure angle in normal plane. So here is this additional step that you want to perform before you go any further. The last but not least is the shaft design. And shaft design is similar, except for the fact, like, let me give you the basic idea of what happens in shaft design. In the spur gear, we just had the radial load and we had the tangential load. So when we design the shafts for the spur gear, we had one force in this direction and other force in this direction. This is for spur gear. Now for helical gear, what's going to happen is, because of the helix angle, we are going to have tangential load, we are going to have radial load, and we are going to have axial load. So what it means is we are going to have moments because of the radial load, we are going to have moment because of the axial load, and we are going to have moment because of the tangential load. So let me give you the shaft design process. So in shaft design, first we need to find out WT, which is the tangential force. Once we know the tangential force, we have to find out the radial force and the normal force. So we have to find out WR, which is the radial force, and WA, which is the axial force. And once we find out the radial force and the axial force, so WT will be known from the equation, which is P divided by VP times CS. Then axial force is WT multiplied by tan alpha, and then there is equation for tangential force, axial force, and the radial force. Radial force is going to be W. So let me draw the free body diagram here. WT, WA, and you're gonna have, if you look at the front view, this is WT. Then there is one force which is going to go like this, which is WR. And then what you do is you have to draw the bending moment diagram in horizontal plane. You have to draw the bending moment diagram in vertical plane, and then find out the moment equivalent, which is the square root of bending moment in horizontal plane plus bending moment in the vertical plane. And then you have to find out T equivalent, which is M equivalent square plus T equivalent square. And last but not least is tau is equal to TEQ divided by pi by 32 times T to the power 4 times D by 2. So with this, you should be able to find out the value of diameter. And I will actually work out a problem start to finish. And in that problem, we will actually find out all these values. So any questions here?
And the second to last question is T supposed to be the point.
Oh, I made a mistake. You're right. This is just torque. So this is T square. T square. Thank you for catching that. Okay. If there are no questions, I would jump onto a problem. So, problem. Design a helical gear. Power transmission is 22 kilowatt. Pinion RPM 1800. Gear RPM 600. Alpha, which is the helix angle, 30 degrees. Pressure angle phi is 20 degrees. Full depth. Number of teeth on pinion. So TP is equal to 24. Both gear and pinion. Both gear and pinion made of steel. Face width, which is equal to B, is equal to 4 times circular pitch. Now this equation needs a little bit discussion. So think about it like this. B is equal to 4 times pi times module. So if you look at pi, which is 3.14, so which means this is approximately 12 times module. Then overhang is 50 millimeters, and Lewis's form factor equation y prime is equal to 0.154 minus 912 divided by TE, where TE is the equivalent number of teeth, and CV, which is the velocity factor, which is given as 350 divided by 350 plus V. So this is given to us. So step 1, we are going to find out WT. WT is equal to P divided by V multiplied by CS. P is 22 10 to the power 3 divided by pi times diameter of the pinion multiplied by N divided by 60 multiplied by CS. At this point, we don't know, so we assume CS, which is the service factor, is equal to 1. So we would say normal duty. Multiplied by 1, dp, which is equal to the pitch circle diameter of pinion, and that is going to be m times number of teeth, which is 24, and I can find out 22 times 10 to the power 3 divided by pi times dp is module. At this point is not known, so I'll keep module as is. Number of teeth 24, n is the speed of the pinion, is 1800 divided by 60, and you can find out value of WT in terms of module. And my answer is, just please take a look at it, which is 9725 divided by module. So this is the answer that I got, 9725 divided by module. So please note, in this particular problem, they have specified the helix angle, they have specified the pressure angle, and they have specified the number of teeth. So this information is already given to us. So next step is we have to find out the value of y prime, which is modified Lewis's form factor. And that is given as 0.154 minus 0.912 divided by TE. So TE is equal to T cosine cube alpha. T is 24. The helix angle is 30 degrees. So cosine cube 30. I think that answer is 37. Okay, thank you. TE is 37. So y prime is, my answer is 0.154 minus 0.912 divided by 37. And that answer is 0.129. Next thing is we want to find out the velocity factor, CV. In this particular problem, the equation for the velocity factor is given to us, which is 350 divided by 350 plus V. V is pi dn by 60. This is going to be pi times d is m times 24 times 1800 divided by 60. which is 13.5 meters per second. So 350 divided by 350 plus 13.5 m. 13.5 m. That is correct. Now the next part is WT is equal to sigma naught times CV times B times pi times m times y prime. And let's find out what would be the value of sigma naught. And for that, we have to look at the data sheet or look at chapter on spur gears, table let's see. So table 28.4. So use table 28.4. Which is again, you will see uh, different values for steel, cast iron, carbon steel, hardened. So you can select the appropriate value for so table 28.4, page 1039. However, in this problem, let me see. They have specified the value of sigma. So in this particular problem, they have given us the value of sigma. Sigma naught is equal to 50 Newton per millimeter square. So this is given. If the value is not given, then you can go to table 28.4 and then you can select the appropriate value of uh, the stress. So which is table 28.4, page 1039. So this is 50. CV is 350 divided by 350 plus 13.5 m. Is it 13? Yeah, it's 13.5 m multiplied by B. It's 4 times pi times module times pi times module multiplied by 0.129. And WT on the left hand side, you would get WT as 9725 divided by m. So as you can see, there is this m floating around on the left hand side and on the right hand side. So this equation needs to be solved using trial and error. So solving equation using trial and error, or if you have a calculator, a programmable calculator that can solve this equation, because you got m floating around at multiple places. And my answer, m is equal to 6 millimeter. And depending upon what is the value of sigma naught you choose, if your sigma naught is different, then clearly your value of module is going to be different. The face width B is equal to 4 times pi times module, which is 4 times pi times 6, which is 76 millimeter. and you're welcome to check my answers.
Not receiving B is 13.5.
Then how much are you? 13.5. Okay. What you are getting? 135.
I was getting 2,000. So
Pi times m times 24, 1800 divided by 60. Yeah, this will be in millimeters. So multiply this by 1000. That gives you in meters per second, because this V has to be in meters per second. Can you please check this if this answer is correct? 13.5 m meters.
if you take pi times 24 times the RPM and divide that by 1,000,
Yeah, and divide that by 60.
not touching the 60 at all,
Or
then
not
you get 15.5.
not touching the 60 at all. Okay, now let me quickly check my. So for that I need to go look at the equation for the CV, and see in CV they are asking meters per minute, or they are asking meters per second. Oh, CV is meters per second. So let me see, 350.
So that's
No, wait, just wait a second. Oh, this is 350. Oh, you are absolutely right. So if it is 350, then yeah,
I agree with Mason.
this is, yeah, meters per minute. So because in this problem, they give us the value of CV here. And in this equation, this V is meters per minute. So in this particular problem, please note there are some values that are directly given to us. One is sigma naught, which is 50 newtons per millimeter square, and CV 350 divided by 350 plus V. But here V is not in meters per second, it is in meters per minute. That's why it is 13.5. Now, can you check my answers to see if they are making sense? Any questions? Yeah, 13.5, good, meters per, fantastic. So substitute those values, and please see if my module and my face width, they are the same. Moving on to the next step, which is the diameter of pinion, dp. Which is 6 times 24, which is 144 millimeter. The number of teeth on gear is equal to 3 times 24, because please note, speed of pinion divided by speed of gear. Speed of pinion is 1800, speed of gear is 600, so the gear ratio is 3. So next, step 2, determination of dynamic load. is WD is equal to WT plus 21V B times C cosine square alpha plus WT cosine of alpha divided by 21V square root of BC cosine square alpha plus WT. And WT value 9725 divided by M, which is 9725 divided by 6, 1620 Newton. So WD is equal to 1620 plus 21 times. Now here you need to check the velocity. So if this velocity is in millimeters per second or meters per second or meters per minute. So I want you to go to the table from the textbook and just quickly refer to the equation, and I'll tell you the page number. So 1040 spur gear. Now the reason I want to point this out here is in this particular problem, for helical gear, if you look at the equation, they don't define the terms. So they say the terms are same as the spur gear, but this V has to be in meters per second. What that means is this V will be 13 point, what was the velocity?
13.5 times M.
Times 6 divided by, so this will be in millimeters per minute. So let me see, 13.5 it was meters per minute, right? Meters per minute. This needs to be divided by 60 meters per second. So this will become, so please, I want you to make this correction or make this change. Make sure that you use the appropriate values of velocity. Now then the value of D is 76 multiplied by the value of C multiplied by cosine square 30 plus 1620 cosine 30 divided by 21 times 1.35 multiplied by square root of 76 times C cosine square 30 plus 1620, and to find value of C, we have to go to table 28.6. So go to table 28.6. And on 28.6, there is something that I just want you to think about it a little bit. So here, what you have is, you have the pitch line velocities in meters per second. For that particular pitch line velocity, you have a particular value of tooth error action that is recommended. So for an example, in our case, our pitch line velocity is 1.3, which is in between 0.09 and 0.08. So I can say my error action. So now I want you to, we did not use this table before, so I want you to note this. So here is a slightly alternate approach. So note, to find tooth error action, pitch line velocity Vp is 1.3 meters per second. Refer table 28.6. On table 28.6, you would observe for pitch line velocity, and you have tooth error action. So 1.25, 0.092, then it's 2.5. This is 0.08. So since our pitch line velocity is in between, I'm going to assume the error action at 0.085, as our pitch line velocity Vp is 1.3 meters per second. Now for this 0.095, there is another way of determining the error action. So you can refer table 28.7, and for 28.7, you would notice that there is module M, and for module there are different grades of gears. So there is first class commercial, carefully cut, and then precision. So in our case, module is 6. So when the module is 6, first class commercial is 0.06, carefully cut 0.03, and precision 0.017. So one thing I want you to think about is, there is different ways of finding out values of error correction factor. The third approach is, you can refer to table 28.5, and this is a table that we referred when we solved the previous problem. This table is dependent on material. So if you have steel, and if your form is 20 degrees full, it gives you the values of C for different values of error action. So this is the error action, and you get values of C here. So 0.01, 0.02, and so on. So as you can see, what I have done is I have selected please note, this is a selection. I have selected 0.085 because my pitch line velocity in this particular problem is 1.3, and I used table 28.6. So my error action is 0.08. For this 0.08 error action, steel to steel, I would say the value of C is 912. Now, if someone says that what I want to do is, I want to look at the module based error action. So the person says my module is 6. And for this 6 module, I'm going to assume maybe precision cut gears. So I'm gonna, my gears would be precision cut. So for the precision cut gears, this is going to be my error action. And for 0.017, the value of C is 114. Are you with me so far? I mean, this point is very important because next step, whether the gear design is going to be safe or unsafe, depends upon how you choose the value of C at this stage. So let me just repeat. So in design, you have multiple ways of finding multiple factors. Now, there is no right or wrong approach. So I want you to go to page 1040, page 1040. And there are 3 tables. One is table 28.5, then table 28.6, and then there is table 28.7. 28.5 table gives you the material combination, pressure angle, and the deformation factor in terms of error action. Table 28.6 gives you the error action that is dependent on the pitch line velocity, and 28.7 gives you the error action depending upon module. So you can find out the tooth error action using table 28.6 or 28.7. You can use the error action using 28.6 or 28.7. Now, as you can see in the problem that we are solving, if I were to refer the module based approach, then my tooth error action is 0.017. If I use the velocity based approach, then my error action is 0.085, which is in between 1.25 and 0.25. And when I take these error actions and go to table 28.5, I get completely different answers. In one case, I get 114, and in other case, I get 912. Are you with me so far? Now, here is what can happen. Let's go back to the equation that we are trying to solve. And then my point would be clear, because I know that this is something where the students can get confused. Now, what I want you to do is, I want you to substitute value of C. Value of C is equal to 114 and value of C is equal to 912, and find out different values of WDs that you get. And you should do this exercise just once, and that will make my point clear. What is, yeah, question?
In the WD equation, is there supposed to be, is the square root supposed to be added or multiplied?
Square root multiplied. Let me see. Yeah, added, sorry, 1.35. This is added. Thank you, added. So what do we want to achieve? For our gear design to be safe, WD should be less than WS. Do you agree with me? So now you tell me, given a choice of C is equal to 114 and C is equal to 912, which one would you choose? And answer is not that straightforward, because what you have is you have the term which is dividing and in square root that includes C, and you have a term which is multiplying and getting added. So I would encourage you to do this exercise and tell me two different values of WD just once for this exercise. That way next time when you do it, you know what approach to follow. So yeah, just do this one for me and tell me WD for these two different values of C. Online students, did you understand? So depending upon assumptions you make, depending upon the error actions you choose, depending upon the table that you refer, you would get two seemingly different, very different values. But what I want you to do is just once, please tell me the values of WD for two different values of C that we just found out.
I have 1645, the first value, and then 1741, the second.
So you have gotten these two values. Are you with me so far? So depending upon what error action you choose, you can have WD is equal to 1625, or you can have WD as 1741. No matter what you choose, at the end, for gear to be safe, WD must be less than WS. So what we want to do is we want to find out WS in the next step. So step 3, determination of static load. And here what we want to do is we want to find static load. We have to again go back to the table, and the material is steel, so we need to select the hardness and we need to select the value of sigma E. So what I'm going to do is I'm going to use BHN 400 and sigma E is equal to 700 Newton per millimeter square. And this comes from table 28.8, page 1042. And with this, I would find out WS is equal to sigma E times B times pi times module times y prime. 700, B is 76, right? Pi 6, I think 0.129. And with this, tell me what answer do you get? Kilonewton. Is that right? 130 kilonewton. So which is much greater than WT. So design is safe. Now, caution. Just out of curiosity, why did we get 130 kilonewton? We got 130 kilonewton because I tried to be smart and I looked at the maximum value of BHN, which is 400. That gave me the maximum value of flexural endurance limit, which is 700. So this is like an overkill for this problem. It is not really required, but I didn't want to go back to the design, iteration of starting with 150 BHN, which gives me like 252, and then all the way iterate just to make sure my WD is less than WS. So you are welcome to choose the lower value of BHN, but in case the design fails, in case the static strength is less than the dynamic strength, then you should be prepared to increase the value of BHN so that at the end, dynamic load must be less than static load. So dynamic load calculated in step 2 should be less than static load calculated in step 3. So just to be on the safer side, I went all the way to 400 BHN. But what that means is the gear will be very expensive because of the heat treatment that the gear needs. And unfortunately or fortunately, this is not needed in this case, because you can see the static strength is 130. And if you look at the actual load, dynamic load, which is about 1.6 or 1.8 kilonewton. But so this is like an over design. It is not really required, but you can, if you want to eliminate the iterations, you can do this. But sometimes when you go to industry, cost is one of the concerns. And at that time, you want to kind of balance the cost versus the size versus the dimensions. So at that time, you may be asked to choose a gear that does not have expensive or an extensive heat treatment. And you can just go with a BHN of 150 or 200 or 240. And I think that would still be sufficient in this problem. Now, there is one more point that I would like to make here, that suppose if you work out the problem, and here the question is which C value I should choose. Should I go with this C value or should I go with this C value? Now, understand this dynamic load, we want it to be low as compared to the static load. So it is advised that if you want to minimize your iteration and frustration, choose the low value of C that will give you a reasonable value of dynamic load, and that will actually make your design safe. But what that means is if you are going to go with lower value of C, your error action would be less, which means the amount of or the cost related to manufacturing of that gear would slightly increase. So these are the balance. These are 2 or 3 things that you want to balance out when you go with the design. So again, these iterations may be good to do when you go with the actual design. Now the last part is step 4. Is determination of wear load. And this is WW is equal to dP B Q K divided by cosine square alpha. Now please note, wear load is always calculated for pinion. So dP is equal to 144, B is equal to 76, Q is an external gear, VR then we have to find out the value of K, which is sigma ES square sine phi divided by 1.4 EP EG. Now since the pinion and gear, they are made up of steel, gear and pinion, sigma ES is 618 square sine of phi n. To find phi n, we have to use the equation tan phi n is equal to tan phi cosine alpha, which means tan inverse of tan phi. Phi is 20 degrees, cosine 30 degrees. That gives me phi n, and then find sine phi n from here. Then substitute sine phi n 1.4. The Young's modulus for steel is 200 10 to the power 3 plus 1 divided by 200 10 to the power 3. That gives you value of K. Substitute these values here and your WW should be greater than WD. And that is how you would just make sure that the design is safe. Any questions? Any questions, concerns, ideas, doubts? Last step is for the shaft design. So WT is equal to 1620 newtons. WA is equal to this axial load, which is WT times tan alpha, is 1620 times tan 30, which is 935 newtons. Now in this particular problem, it's said overhang. So gear has the overhang of 50 millimeter. What that means is this gear is like this. So what you do is, if this is your A, you're gonna find out MH and MV. MH is WT times 50. MV is WA times 50. M equivalent is equal to square root of MH square plus MV square. And then you will find torque equivalent is square root of M equivalent square plus T square. And T, you know from the equation, power is equal to 2 pi nt divided by 60, 22 10 to the power 3 multiplied by 60 divided by 2 times pi times 1800 is equal to torque in Newton meter. So this torque will get substituted here, and then tau is equal to TEQ divided by pi by 32 times d to the power 4 d by 2. From here, you can find the value of d, and my answer is 31 millimeter. So this is how you design the helical gear start to end. Also in the textbook, there are some good problems that are given on the helical gear design. I would encourage you to take a look at these problems. And in next class, I'm gonna talk about the bevel gear, and then I will work out the problem for the bevel gear. Now, please understand the bevel gear design process is also similar. We take the bevel gear and then try to convert that into a form of spur gear, and then follow the exact same principles and same equations. So what is different between the spur gear, helical gear, and bevel gear? So next class, we are going to do bevel gears. The bevel gears can be at an angle. So here, as you can see, the input shaft and the output shaft, they are perpendicular to each other. So input shaft and output shaft can be at an angle. So bevel gear could be something like this. So unlike spur gears and helical gears, the gear shafts could be intersecting and could be at angle. So if you want to transmit the power not parallel to axis, so in spur gear and bevel gear, spur gear and helical gear, the shafts are parallel. In the case of bevel gear, the shafts can be at an angle which could be 90 degrees or it could be different. And you can have the regular bevel gears. You can have the spiral bevel gears. And depending upon the applications, depending upon amount of power that needs to be transmitted, the angle at which the power needs to be transmitted, you use different types of gear design. But bevel gear, again, the principles are simple, steps are exactly the same. In the next class, what I would do is I will give you the nomenclature for the bevel gear. I will give you the recipe for bevel gear design, which is exactly same as spur gear and helical gear design. And then we would actually work out a problem on bevel gear design, which I think is your homework problem. So with that, I'm going to stop here. If you have any questions, I would be happy to answer.
That's what a rear differential is, right?
Yeah, that is the real differential. So any questions from my online students?
shaking ours. It's not been like compiling so much Excel data. I'm trying to like see graphs with like garbage data. Most of it.
No, actually, doing PCB is a good idea, but before that, you can just try this.
What do you do? At the first DM or
What? You make the PCB Gerber file. Did you make the Gerber file?
no.
You just send me the outline, right? Yeah, that outline is not right.
Oh yeah, that's what I was waiting.
Yeah. Your outline should follow the outline of the small drone.
So okay, we just want it to be extended. That's where it was.
Don't extend it. It will still fit.
Pins will be in there. How do we do?
It will work.
Like I don't think that software can actually recognize the pins. Like if I have any pins hanging out of the outline, it'll be shouting at me.
Okay, I just want to let you know that someone contacted me regarding engineering positions. So I put that contact information on announcements. So you are welcome to contact them and send your resume if you are interested. What? You send the resume? Good. Don't forget to mention that you are in my class. That way they will actually see your resume. You can't spell PLCs.
I know how to spell PLCs. Can I spell it?
Well, they have multiple positions, so just go talk to them. You apply. Oh yeah, no harm in applying, right? What I'm highly recommended by Dr. Ishka. Okay, I'll start in few minutes. Just trying to get.
So how do we implement it to the motor machine?
2 minutes. Yeah. For cars.
Any class that deals with ARM processors.
ARM processors. Yeah, just a second.
Professor,
Yeah.
can you show the combinatorial filter solution?
Yeah, of course. Just bear with me for a second. Get ready for today's class. And I will show you complementary filter solution. I will show you the motor mixing algorithm. If you got your Mambos, then we can program the Mambos. Yeah.
Yeah, with regards to Mambo, like we have two Mambos and both of them, like 3 motors are working and 1 motor is functioning. So is it something related to the flashing of it? We have to flash it again. Like why would that happen on both the Mambos?
I have no idea. So, but if you want to replace, if you want a replacement Mambo, I would be happy to give you a replacement. Or if you want just to, if you want to replace the motor, I can give you the screwdriver and the motor. Replacing screwdriver and motor is not difficult at all.
Yeah, I think that would be better.
Yeah, so I will give it to you. That's no problem.
Yeah, thank you.
Just let me set up Zoom onto this. Okay, any questions before I begin? So my plan today is to talk about a little bit of theory related to the stability, controllability, give you some examples and explain you in simple terms, what do we mean by controllability and how can that be implemented on a simple platform such as Mambo. Then next part, I'm going to talk about implementing the complementary filter, and then hopefully most of you have found the solution for complementary filter. If not, I will show you how simple that is. Then I will try to give you some hints on implementing the hover control, and my hope is by Thursday at least some of you will have a hover control implemented. It's not difficult. So I'm going to start recording.